Welcome everybody to today's lecture. My name is Jens Dittrich and today we will be talking about query optimization. This is part one. There will be two parts. The second part after the Christmas break. So here's the agenda again. Where are we? So we are here in this row, how to compute complex queries at scale. We talked a bit about query processing last time. Today we will look at operator models, pull and push, if time allows for it. We will, in the first phase, mainly look at rule versus cost-based optimization and the challenges that are involved in that. If you already attended my big data engineering lecture as part of the bachelor's here at Saarland University, there I already covered some of that, so from a different angle if you wish. Today you will hear a little bit of a different story about the same techniques that give you a different perspective on those techniques. So if you attended that lecture, you will learn a couple of new things. If you didn't attend it, still you will get the entire story and understand what rule and cost-based optimization is about. So for both types of audiences, the lecture hopefully works. With that, let's start. I will be available on Discord again, on the text channel lecture and in the break, and after the lecture in the audio channel as well, but during the lecture, the text channel. Okay, so first let's look at an overview of what we are talking about. So that is how typically a query optimizer architecture is embedded into a system. And you see that in many systems, it's something like that. In the context of a database system, we have a SQL statement. Whatever SQL statement on top. Select from where, whatever, can be as complex as you wish. And then there are different components and steps that have to be done. And one is there's a query parser. So the textual representation has to be parsed somehow and translated, which is often done along the lines of something resembling relational algebra. You should know relational algebra, that's covered in the undergrad lecture. We'll look at that in detail. Many optimizers do that, but there are other ways of doing that, and that will also be part of today's story. Yeah, then there's the actual query optimizer that does the magic, that has to come up with an efficient way of computing the results to that query. We will look at that. And the query optimizer interacts with a so-called catalog. We mentioned that briefly already last week, where I said, okay, the catalog contains all the metadata in the database system. It has information on which tables exist, what are the attributes available on those tables, what are the domains, are there any foreign key constraints already available, how much data is there, statistics, how many tuples exist in that specific table. All of this metadata, information about the actual data, is stored in the catalog. And the query optimizer can freely query that catalog. And fun fact, the catalog is a database. It's a database with tables, relations, just as a normal database, but it's kind of built in every database system. Yeah, and then basically there are two paths to follow in query optimization. One is optimizing along so-called pre-compiled modules, basically resembling physical operators or basically resembling principal algorithms, like a simple hash join. We talked about the simple hash join algorithm. That could be part of some module, and could be that the query optimizer decides to link some of these modules together to evaluate a query plan. And that is something we call, in the end, plan interpretation. So a little bit like a script. Yeah, that's basically certain calls to certain library functions that are performed by the query optimizer. The other option, and that has become much more popular in the past 10 years or so, is to generate code, actual program code, and then that code is executed. That has a couple of advantages, in particular in the context of a main memory system. So back in the old days, I would say, if where databases operated mainly on slow hard drives, it was fine to do the computation against precompiled modules because the effects of generating code wouldn't show off that much because the hard disks would slow down the entire system anyway. The disks were the bottleneck, so whether you would go down the left path or the right path wouldn't make so much of a difference. But in the context of a main memory system where I/O is so much faster, I/O to DRAM or other similar media, there it makes a huge difference, and the code execution plays a role. So you might be reminded of a similar picture you may have seen if you think about a standard compiler, a C++ compiler, or whatever language you're programming in compiler. Well, what does a compiler do? It takes a whatever C++ program, that's a text, that's a query if you wish, and translates that by parsing it, and then there's a couple of steps, but also involves some sort of optimization, and eventually it generates code. So there's a strong similarity to what general purpose programming language compiler do. However, the difference in database being databases are way more domain specific. So what we can express in the language is much tighter and much more restricted, not in terms of Turing completeness, that's a different story, but in terms of what people actually do with the language. And often these domain-specific things in a language allow us to do certain optimizations that you can't do in a standard compiler. Okay, so that's the overview of a compiler. And now let's look at rule-based versus cost-based optimization. So those are two principal approaches to optimizing queries. And what is a rule-based optimizer doing? And basically, again, you have a SQL statement. I stripped it down a little bit, so I'm not showing group by, having, and whatever nested queries. Just assume it's a simple select from where statement. And you have a couple of attributes you're projecting to, A1 to AN. You have some relations, R1 to RK, and you have a where clause. And I hope you remember from your undergrad lectures that whatever's in the from is conceptually a cross product. So what we're seeing here, so what we're seeing here is R1 cross R2 cross and so forth till RK. Yeah. So basically, conceptually, the statement says, okay, build the cross product across for these relations, and then filter out all the tuples that fulfill a certain predicate. That's expressed in the where part of a SQL statement. And once you filtered out those tuples, project to those attributes only, A1 to AN. That's what's happening conceptually. Of course, that's not how you must execute it. There are more efficient ways, but conceptually, that's how you read a statement. And basically, you can express that in relational algebra as follows. You say, okay, that's my input, cross product over those relations. Then you filter that out. Yeah, that's a select operator, selection operator. And then you project it to those attributes. Yeah, that's basically what a query parser could be doing, translating this SQL statement to some sort of relational algebra. And I wrote on top here, that's textbook style translation. You see that in many textbooks, including the Kemper textbook. And we will later learn that there are other ways of doing that. But that's what you find in textbooks and many explanations. And then basically, you perform certain steps. The first is from the canonical form, you build a so-called canonical form of a query. And basically, what you do is this expression on the left, relational algebra, you can basically write it down as a tree, as a binary tree. So where you first do a cross product on R1 and R2, that's basically this one. Then you continue building the cross products up to RK. So all of this part is then the input. Then you do this big filter on the predicate, and then you project. That's a valid expression in relational algebra, just displayed as a binary tree. Yeah, and from that, you can do certain things. Here's an example of what you could do with such a query. So assume we have the following query selecting only one attribute from those relations. You see there's a join condition on those relations, a.id equals b.dz, and there's a filter on the name attribute of relation A. Yeah? The name has to be Hugo for whatever reason. That's our query. How would we translate that? So here in relational algebra, we could write it like that. Our predicate is this one. Here's a cross product, here's projection, everything fine. And basically, the canonical translation puts it into this tree. That's a tree. Huh? So what can we do with that? That is what we call rewrites, rule-based rewrites. And there are a couple of rules that can be applied there. So basically, the idea is to come up with a tree that produces exactly the same results. Yeah? So at all times, all the rewrites I'm showing, they must produce the same result set of the query. Otherwise, it doesn't make sense. I want to create in the following a relational algebra expression that I hope to be more efficient later on. That helps me create a more efficient plan in the end, and that's what I'm up to now. So basically, when I start with something like that, now what I can do is I have a conjunct here. This basically there are two parts in this predicate. A.name equals Hugo and A.id equals B.dz. I can break that up into two separate predicates if I wanted to. And that's what I'm doing here. I say, okay, I first filter on that one, and then I filter on that one. You could also do it the other way around. It doesn't matter. It doesn't change the result, but it's semantically equivalent to what I'm doing on the left. And that's one possible type of rewrite. And why would I do that? The reason is that I can do different things with the different parts of this predicate. Now I could say I push down this filter. Here I wrote it down on the left again. This filter is actually only, this filter is applied on relation A. Yeah? So why do I only do it here? Why do I filter the data out here? I could directly filter out the data when reading the tuples from A. And that's why this is called a push down. I push down the selection. Immediately after this A relation, I filter out the tuples that qualify, and only then I go into the cross product. Which, if you think along complexities, means, well, it doesn't change the complexity of the cross product. The cross product will always have a square complexity, but the input size to the cross product will change. Rather than inputting all the tuples from A on the left, here in this scenario, I only input the tuples that qualify, which is hopefully much fewer tuples that qualify. And with that, the expected runtime of this cross product goes down. So that's a very important type of rewrite, and I think I also briefly mentioned that in the big data engineering lecture. So filter out data as early as possible. It's an important rule. And another thing that you could do in this situation, so again, now we're here, that's what we had on the previous slide. Now we still have this condition here, and there's a rule saying, well, if you have a cross product, and on top of that is a selection, that is a so-called joint predicate. That is a joint predicate because, this is a joint predicate as this part here refers to the left input of the cross product, the A.id. And this part here refers to the right input of the cross product, that's a B.dz. And then there's a rule saying, okay, if you have a situation like that, the selection followed right after the cross product, you can rewrite that to a join. You say, okay, that's my join. And the join gets that predicate, that joint predicate, and that is how I express it here. And of course, later on, the hope is that the join can be something better than the square complexity, and most joins can do that. So that's another heuristic rewrite, hoping that the efficiency of the plan later on will be better. Yeah, that's another type of rewrite I'm doing. Here's another variant of pushing down things. So before we push down the selection, but I could also push down projections. So how does that work? So here, in the overall plan, I only want to display the title. So the question is, well, why do I keep all the other attributes of the relations if in the end I only project to title? So in this situation, you can replicate projections. Basically here, we insert additional projections. And here in the example, I insert a projection to title, ID, which means after the selection, after having filtered out all of the qualifying tuples here, I only keep the attributes title and ID, because those are the only attributes that are actually required later on for query processing. Why ID? Yeah, well, ID is required in this join. The join predicate references that. And title, well, that's what I want to output in the end. So by that, I can reduce the amount of data I ship around. In particular, if you think about a column store. Column store understands that, well, I don't need these tuples anyway. I don't need these attributes anyway. You can filter them out directly. So in most column stores implementation, you get that for free actually, because you only refer to the columns you need for doing any computation. We will look at that later on. There are a couple of other options you can do in column stores, but for the moment, in the general relational algebra tree, there's something to gain here by projecting out, by making tuples less wide, narrower, much more narrow, and that will avoid shipping around a lot of data. Yeah, so here again are the most important rules. There are many other rules, and most database vendors keep those rules as a secret because they may make a huge difference in query performance in the end. But the most important rules you should really remember, and one is you push down selections and projections. That's also called predicate push down. You combine selections and cross products into joins. You want to have as many joins as possible. Whenever there's an opportunity to have a join, get rid of the cross product. And third is you insert additional projections. Those are the most important rules. Yeah, that's rule-based optimization. Now let's look at cost-based optimization. What does that do, and what are the challenges involved? So once you have such an expression in relational algebra, it's not obvious what the order of execution is. So assume the following situation. Assume you have three relations only, A, B, and C, or A, C, B, I put it in this example. And assume that all of these relations have 1,000 tuples exactly. Yeah, that's 1,000 I'm depicting here, here, and here. So the cardinality of each relation, that's the terminology, the cardinality is 1,000. Well, and now if you have binary joins, what can you do? Well, you could first join C and B, and then the result was A. That's one possible plan. Or you first join A and C, and then whatever comes out of that, you join it with B. That's depicted here on the right. That's plan number 2. But what is the difference? Well, the difference is the amount of intermediate tuples that are generated. Yeah, that may lead to more computational effort, that may lead to more data you have to keep in intermediate structures, data you have to ship around. And there you see there may be a difference. You see here, those are artificial numbers. I just made them up, but that's a situation that occurs frequently. You see here that, okay, here the number of intermediate tuples, the number of tuples generated by plan 1 by joining C and B is 100,000, which means this join between A and the result of C join B has two input sizes, 1,000 and 100,000. And however, if you look at plan 2 on the right, you see, okay, here the join of A and C only has an intermediate result size of 100. 100, yeah? 100 from the left into the second join, and 1,000 tuples from the right, from relation B, is the right input here. Right input 1,000 tuples, left input 100 tuples, the intermediate result. So, well, again, it depends on the actual runtime costs of those joins, but you see already, well, that's a difference, right? Times 1,000 smaller intermediate result just by changing the join order, and that may make a huge difference in the query optimizer. Whether you come up with plans with join orders on those queries that early on only produce very small intermediate results, or that tend to keep very large result sets until eventually coming down to very small result set sizes. And of course, for both plans, the final result is the same. And all of these query optimization techniques we're discussing, whatever these techniques do, the final result will always be exactly the same, no difference whatsoever. But the question is, how do you get there? How do you get to a result? Yeah, and that leads to this problem, join order. And another problem that you have in the query optimizer is how to access the data in the first place. So when we talked about indexing, we presented different index structures to you, B trees, hash tables you know anyway, but then even the different types of B trees, unclustered clusters and whatnot. There are many options. And eventually, the query optimizer will make these decisions automatically. Yeah? The idea of a database system is not that you as a user say, oh, please use the index, or please use this physical join operator, this hash join, use the external sorting there and do whatever, hash table there. No, that's not the idea. Whatever you do as a user, you always just send a SQL statement, and the query optimizer has to decide itself whether to use the index, whether to use join algorithm X, Y, Z, how to come up with a plan. So that's all automatic. And in the context of indexing, that means it has to make a decision. So if you see something like this here, there may be different options. Yeah? So there may be the option to scan this stuff, to scan relation A. That's what this visualization is supposed to be showing. There's some data layout on A, yeah? Whatever. Maybe it's a row layout. And then basically a decision could be to scan relation A, scan each and every tuple. For every tuple, check whether it qualifies, whether it fulfills the predicate. Yeah, and if that's the case, you pass it on to the next step in this plan, and so forth. That's one possible translation, but of course there are others. You could say, well, these two operators together, well, I could rewrite them against an index axis. I could say, well, I have an index. I happen to have an index on A available anyway, and that's what this is supposed to be doing. This upside down tree. So it's some sort of tree index, for instance, on relation A, built on attribute name. So I used attribute name as a key in that index. So I can look it up directly. That's a point query. Yeah? So the optimizer has to make a decision to rewrite it against the index. That's very important. And yeah, then there are all these options. You could say, okay, what if I have a clustered index? Yeah, that's why I have these parallel lines here in the visualization. Yeah, the order on the leaf level corresponds to the order on the data pages on disk. That's what we had when talking about indexes. So yeah, the optimizer may choose to use a clustered index. It may choose to use the unclustered index, or there are even special cases when the attributes are completely covered, are completely contained in the index. Then in that case, you don't even have to go to the data pages. That's a situation, for instance, assume you want to know whether a certain key exists in relation A. Yeah? And if you, for instance, build a dense B tree on A.name, we had that briefly when talking about indexes. So if you build a key on A.name, a dense key, then only by looking up the leaf level in the tree, you will be able to answer or to understand whether the key exists, yes or no. You don't have to inspect the data pages being pointed to. And that these indexes are also called covering indexes or index-only plans. Covering index even allows you to add more attributes to the leaf level of a tree. But anyway, there are all these options, and you might wonder, well, that's easy, right? I mean, I have an index, I just use it. What can possibly go wrong? And that's interesting. Many things can go wrong, and many database systems have issues with queries that access an index and are in fact slower than scanning all of the data in the first place. Yeah? So the optimizer believes, hey, it's a great idea. I just do an index access, a point query on the index, and then it's 10 times slower than a scan-based translation of the query. Yeah? You may wonder why is that the case. Well, let's get to that point. And that has to do with estimating the costs of such an index access. Yeah? So if you try to understand what the costs are, if you go to the clustered index again, what are the costs? Well, let's hope that all the internal nodes of the B tree sit in the database buffer. Huh? So there's no costs, no IO costs for fetching this stuff. But maybe you have to fetch the leaf. So that's one random IO to fetch the leaf of the B tree. And then it's one random IO, let's hope it's only that, to go to the store. Is exactly that, yeah, one to the store, and then maybe you have to do ISIM, because if many qualify, well, then you have to scan across those data pages. That's roughly the cost of a clustered index access. For unclustered, it's a bit more complex. Here it depends a lot on how many tuples qualify. And in the worst case, as the order doesn't correspond, the order of the keys in the index doesn't correspond the order of the data pages on disk, it may actually happen that for each and every arrow, every pointer from a leaf level in the tree to a data page, you trigger one random IO. Yeah? If you have only one tuple qualifying, it's one random IO to the data store, but if it's 100, it's 100 random IOs, and that may make a huge difference. It depends really on how many tuples qualify, and that is a huge factor in the overall cost of such a query against an unclustered index. Cover an index, just for completeness, what would you expect? It's one random IO to fetch the leaf, then ISIM. So it's basically equivalent to a clustered index. except you don't even have to go to the data store. So the critical thing are those unclustered indexes. With clustered indexes and covering indexes, the cost estimate, there won't be surprises. That's okay. That's the best you can do. What can go wrong? That's fine. But the problem is unclustered indexes, and that is where some systems really have problems, and that's depicted here on the right. I just wrote down here the different plans I'm showing in this graph. So the scan-oriented evaluation, you scan relation A, filtered out, that's the scan plan, and the unclustered plan. And the cost, there's typically a cutoff. Due to this heavy amount of random I/O, you can basically model the costs of the different plans. You can say, okay, for scanning that, well, I scan everything, filtered out, and that's basically independent of the number of tuples that qualify. If you just look at the scan, of course, the more tuples you push up later on, there are additional costs attached to that. But if you just look at retrieving the data and filtering out the qualifying elements, that's basically constant costs. That's independent of the selectivity. Selectivity meaning the number of tuples qualifying. So what the x-axis shows here is I make a difference whether few results qualify or many results qualify. That's called the selectivity. So basically from left to right, more and more tuples qualify. And that is what makes a huge difference in an unclustered index. By the more results qualify, the more the costs for using the unclustered index go through the roof. Yeah? And then the trick, or what a query optimizer has to be aware of, is that it doesn't this crossing point, yeah, where the unclustered index plan crosses the scan plan. You better get that right. Yeah? Assume you pick whatever in this range the selectivity is here, and you pick the unclustered index in Query Optimizer, and then you're way above the YouTube stream. Yeah? That's the cost you will be seeing, and that actually happens in some optimizers. The question is, why would that happen? Yeah, why would an optimizer make a mistake here? That's something for you to write in the Discord text channel, I would say. Yeah, I mean, if it's clear that, well, if you're till here, you do the unclustered index because you're faster than the scan. And once the selectivity goes beyond this point, you scan. Well, then everything is clear. The optimizer just has to implement this. It has to make an if smaller this point. You do the unclustered index axis. If it's bigger, you do the scan. That's basically the rule the optimizer has to get right. But why would that possibly go wrong? Do you have any idea? Write it in the lecture text channel. Yeah, someone wrote something or not? How could that be? How could the optimizer make a wrong decision here? No idea? I mean, the question is, two of you are writing. I wait for your answers. Okay, one wrote because they underestimate the selectivity. Yes. The second wrote, isn't the total number of tuples that qualify unknown beforehand? Yeah, very good. Is it or is it not unknown? Well, in order to make such a decision, yeah, I have to determine basically the slope of this curve, or the selectivity, in other words. So the function, the magic function that I require to make this happen is, given such a predicate, a.name equals Hugo, I want to know, before executing the query, how many tuples fulfill that condition. without executing it. Just the number, not the concrete tuple, just the number. Is it 42? Is it 3? Is it 7 million? And that is what's called statistics. So I want to know this. I want to have statistics about how is data distributed. Is it uniformly distributed? Is there skew? Are some values appearing more often than others? That I want to know. And in order to make such a decision, I have to know that before executing the query. And that's information collected by an optimizer, or in other words, it's information that must be collected by a cost-based optimizer. Otherwise, cost-based optimization simply doesn't work. Another option, another tiny little hidden assumption, where was that slide? Here, in that slide, I made a similar assumption. I said, okay, assume you join C and B, and then you get 100,000 intermediate tuples, or if you join A and C, you join 100 tuples. That's the same problem. How can I possibly know that by joining A and C, I receive 100 tuples? I either joined it already in the past and I collected that information, or I have some statistics telling me, yeah, whenever you have A and C, you will have that many tuples, or that many are filtered out and stuff like that. So this decision whether to execute plan 1 or plan 2 can only be made if I have those statistics, if I have that information available. Otherwise, no way. I can do guessing, but then it will hardly be a good idea, just guessing a random plan. I won't end up with the best possible plan here. Yeah, so statistics, yeah, either on the selectivities of these joins, or as shown in this graph, how many tuples do I get when I send specific specific predicate? Yeah, and that's a hard part. Collecting those statistics is very difficult, and there's still ongoing research work. Also combining that with machine learning, there's some hope when using machine learning that you can do things there. But that's very tricky, and that's often overlooked because these query optimization algorithms, you will also see that in textbooks, they assume, yeah, you have statistics, someone does that. But if those statistics go wrong, many things can happen. So that's a requirement for these algorithms, really. Okay, so, and now if you look at those plans, and that's basically the slide I showed before, you can think about join selectivities. The join selectivity is defined as follows. So basically, we collect the number of tuples, or we count the number of tuples that are available in the cross product. Yeah? So if all of these relations have 1,000 tuples, basically do number of tuples in C times number of tuples in B. So that's Z, that's 1 million. And then you also count the number of tuples in the join result. That's 100,000 divided by 1 million, that's 0.1. That's the join selectivity. Here's another example. Here we have a join selectivity of 0.0001. Don't get confused with the naming. That's a common thing in discussions about join selectivity. This is a small number. 0.00 whatever is a small number. That's a high selectivity. Small number, high selectivity. Highly selective, meaning only few are selected, few tuples are selected, many of them are filtered out, which means the number is small. Vice versa, if the number is big, that's a low selectivity. Yeah? Many tuples pass, not so many tuples are filtered out. Yeah? That's a bit of a confusion when talking about selectivities. Yeah, so what can we do with something like that? So we have to make a decision automatically. How do we do that? And we do that in the cost-based optimizer. And the idea of this approach is, that's a family of approaches, is you enumerate the set of all plan alternatives. Or if all is not possible, a huge set of plan alternatives. You estimate the costs for each of those plan alternatives, for each plan. How much am I going to pay for that? Costs means not cost may mean many different things. Typically, it's execution costs, so the time you expect this plan to take when actually executing it. So you enumerate many plans. You pick the one where you expect it has the lowest costs, and then you execute it eventually. That's basically the idea. So planning alternatives. It's like going to a supermarket. Yeah? You want to go shopping, you have 3 different supermarkets, and you can factor in the different costs associated. Like, okay, the supermarket is 3 kilometers away. There's some costs for taking the car or taking the bus and paying the ticket. And the other supermarket is 200 meters around the corner, and there's another supermarket 10 kilometers away. Then you could factor in different prices for the same products across the different supermarkets. That's another factor of your cost model you build. But in the end, what you do in your head is, okay, you do the math, okay, if I say in terms of cost, I want to minimize the overall costs. I don't want to minimize, for instance, how long it takes to get to a specific supermarket. If you just want to, for instance, minimize the number of euros you spend, then you can do the math, you can make a prediction, and then you say, hey, it's supermarket 2, the one that's 3 kilometers away. I will go there. And then you actually go there. Then you actually execute the plan. And when you look at the possible plans you have, when you have binary trees, you can compute that using the so-called Catalan numbers. And I want to briefly show that. It's just a bit scary. I mean, it's a tool from, it's an analytical model. And the assumption is that all joins, that all relations are joined with all joins can be, all relations can be joined with every other relation. So basically the argument goes as follows. So when you just look at the structural component of such a binary tree, you see this is a structure we call a left deep tree. Why is it left deep? It's because how relations are joined here is as follows. You take the first 2 relations, that's A and B in this example. It doesn't have to be A and B. But you take the first 2 relations, join them. Then, whatever the result is, you join it with the next relation, C in this example. It can be anything else. And then, whatever the result of this expression is, you join it with one other relation. So you keep on adding relations iteratively. It's always adding one more relation to your intermediate result. That's called a left deep plan. You can also do right deep, of course. It's symmetric on a logical level. But that's one variant in the join structure. Another plan that's not left deep, and that's also sometimes called bushy, is a plan like that. Here, this pattern is broken. It works till here, but here you see this is not about just adding one other relation. You see there's a join of D and E, and then whatever the intermediate result is, that's joined in a left deep manner to the left part of the plan. So many of these structural trees are possible, and this problem occurs in many places in computer science, and can visually be expressed as follows. So here I try to visualize the things that reoccur using the same colors. So basically, if you just look at what are the options if you only have 3 relations? That's this first row. 3 relations, that's what I just showed you. So you basically first do these 2 on the left, and you join it with the remaining relation, then you end up with something like that. Or you do it basically mirrored and say, okay, I first join those 2 on the right and join it with what's on the left. That will be the right deep plan, that will be the left deep plan. Those are the options you have when joining 3 relations with a binary join tree. Now, if you look at problems of size 4 relations to be joined, those are the options that exist. So basically, you have whatever you can do with a subset, a subproblem of size 3 happens in the orange box displayed above. And then whatever the result of that is, you join it with the remaining relation. That's one option. Or again, the mirrored solution is shown here on the right. You first place this orange box subproblem of size 3 on the right and then join it to the left with the remaining relation. Or you do this approach where you say, okay, I have it balanced. So I have a subproblem of size 2 and another subproblem of size 2. You join it there, and there you go. Those are the options. And with that, you could visually, recursively show the options you have. So here, this could be solved by whatever subproblem of size 4. Those different options joined with the remaining relation. That's a mirrored approach. And again, here you partition it into a problem of size 3 and 2, solve them independently again by the options you have, or you do it mirrored. Yeah? And that's basically how you visually construct the options that are available for building binary trees. Yeah, and basically one observation is they're commutative. So here I showed you, well, whether I first do 2 and 1 or 1 and 2, whether it's mirrored or commutative, in other words, and that the same happens here for this one and that one. So you could say, well, that's kind of the same. Yeah? Do I really want to enumerate all of those? And we will get to that later on, why it will make sense or it does not make sense. Okay, but then basically the number of those structural trees, yeah, of these structures that are available that can be generated by a certain problem subsize are computed by the so-called Catalan numbers, and that is a formula. You can also write it like that, or you can also write it as a recursive formula if you want. Here are some example computations. So that's a problem of size 1. There are there's one possible tree. Here it's 2, and here it's 5, and so 14. Here it's 14. Yeah? So it goes pretty quickly through the roof, these numbers. And well, that gives us the number of different structural trees, yeah, with the Catalan numbers. The number of structural trees that can be scribbled here in this purple box, basically. But still, what is fixed here, what I didn't consider so far, is the order of the relations. How do I input the relations into that structural tree? So I said A, B, C, D, E, but that could be any order, right? So if you make it more tangible, again, look at an example where we have 3 relations. Maybe I just get rid of the camera for the moment. So if I have 3 relations, so we have these 2 possible structural binary trees, and those are then the orders that are possible. I could input those as A, B, C, A, C, B, B, A, C, B, C, A, and so forth and so forth. So this is Fakultät in German, whatever that is in English. What is Fakultät in English? Does anyone know? To look that up. Fakultät. Here we go. Factorial, of course. Yeah, of course, factorial. Yeah, so sorry for that. So the factorial, yeah, that is 3 factorial here. Yeah, 3 times 2. 3 times 2, that's 6 different orders are possible. So the number of relations, factorial, that is the number of different orders you can put here under that tree. And the same happens here. So basically, it's the number of structurally different binary search trees times the number of relations factorial. That is the overall number of join trees you receive. Yeah? So that's the overall formula here. Yeah? Number of different relations factorial times the Catalan number for that many binary search trees. Yeah, and well, one thing you might wonder, okay, and then, but why would that make a difference? Because in that discussion, we made this split here. Maybe that's something for the break you can think about. So if you look at these different plans, so what's the difference in those plans? Again, it's about on these ACB relations. And note that here, in contrast to what we had before, both intermediate results have the same size. So we have 100,000 tuples here, and we have 100,000 tuples there. So what I just showed to you in the number of different plans that are possible, yeah, those 2 plans are counted. But why would I count them if they have the same intermediate size. Why would that make a difference? What would be a case? Or so should I count them as separate plans, or should I say, well, it doesn't really matter. They have the same number of intermediate results and they're symmetric, so basically put them aside. And that's basically what I showed here in this graph here. Where was it? Yeah, it's basically this case here on top where we have three inputs where I say, okay, you either count them separately or you do it like that and say, that's the same plan, right? It doesn't make any difference. Who cares? And then when enumerating the different relations, when writing down the orders of relations down there, you will get the different plans. So it doesn't make a difference. So think about that in the break. Why does it make sense to keep separate plans like that? Or why would it make sense to not keep these plans as separate plans and say, okay, I just treat them as one plan. I don't really care. That's your exercise for the break, and we will continue 12 minutes past 1. See you then. Okay, so what's the important difference here? So if you look at the iPad here, that's an even smaller problem. So you have two different joins. You have a join where the left input is A and the right input is B. That's this one. Or the other join where the left input is B and the right input is A. Two different plans, two different options. Why would it make a difference? What could be the difference? The only difference could be if the cost model is asymmetric. If this, let's call it whatever, that's plan 1 and that's plan 2. So if plan 1 has a different cost when changing the order over plan 2. And why could that be the case? Well, just if you remember simple hash join. In simple hash join, on the left input, you build the hash table. And what associated with that is you have to keep the stuff in main memory. So if the left input is rather big, that may make a difference. If you go back to our slide here, here's a situation where that may occur, particularly if this in plan 3 here on the slide. Yeah, the left input 100,000 tuples. There you have to put 100,000 tuples in the hash table in main memory, whereas here in this plan is only 1,000 tuples, and then 100,000 tuples are probed against the hash table. So that may make a difference in terms of runtime complexity. Maybe not so much, because more or less constant lookup time in the hash table and insert time, but main memory costs may make a difference. So the simple hash join is an asymmetric operator, asymmetric algorithm. What if I do sort merge join? Would it make a difference? Any ideas? Sort merge join. Talked about that, I think, last time. SMJ is the abbreviation for that. Any ideas? Write it down in the text channel. Whether I do plan 1 or plan 2 and I use sort merge join to execute the join. Will it make a difference? Yes or no? No idea? So if you use sort merge join, merge join, is it asymmetric or symmetric? Does it make a difference whether A is on the left or on the right? No, it does not. Also, it's symmetric. That's a symmetric operator. That doesn't matter. Yeah? But that's in contrast to something like simple hash join. And so the plans you enumerate, it depends on the operators you're using. If your join operators are symmetric, you don't have to enumerate those plans twice, because that will lead to the same cost, and that will ruin, that will increase the search space artificially without any need for that. Yeah? So if you only have symmetric operators, you can shortcut the enumeration. But if you also want to consider asymmetric operators, then it makes a difference. So that's important to consider in these situations. Okay, with that, let's look at a concrete algorithm that does the cost-based optimization. And the scenario I will be looking at in the following is following. So I was asked to remove the camera whenever possible. It's not on the way here. So here you see an example of a SQL statement that we will look at in the following. So here a couple of projections, a couple of join conditions written explicitly in SQL. So A joins B, D joins B, C joins D. You have some additional filter predicates, and that's our statement. Now what we basically do, what we create with that is a so-called join graph or query graph. That's another term for that. And the idea is basically in a graph, each relation becomes a node. I think I can move that in for the moment. So each of these bubbles is a relation. Here's just if you look at in the middle here, that's a simple variant of a join graph. And then you say, okay, whenever there is a join condition, a join predicate specified among two relations, you insert an edge. Those are the green edges here. From A to B, that's this one. From D to B, it's this one. From C to D, it's this one. We have three edges here. The other possible edges also marked here. You can also leave them away, but basically what the other edges say is, well, that's a cross product. So if you wanted to do anything with looking at A and C, you don't have a joint predicate, but you can, yeah, you can do a cross product. You can always do a cross product between two relations. So basically, only the ones where you have an explicit joint predicate, they are marked by a thick yellow line. It can be any color. Here I'm using yellow. Basically, here's a matrix of possible operations you have. Basically, adjacency matrix, where you say that, okay, here A and B, there's an edge, A and D, there's no edge, A and C is no edge, so no edge implicitly translates to A, cross product. I can always do a cross product. So that's the first step. The second step you do is the following. You say here, and let's look at the right, that's an extended query graph or join graph. You say, hey, in addition to those join conditions, I not marked here only by having this edge, this line among the two nodes. You also write down the concrete joint predicate. Yeah, you annotate this joint predicate. That may help later on. And in addition to that, you also annotate the graph with filter conditions that only apply for a specific relation. So in this case, we have a filter A1 equals 42. That's here in the sequence statement. That's there. Should we write it down in this query graph directly? And then basically we have a very nice visualization of what the query is about to do, except the projection part. Yeah? So we're not saying here what are the attributes projected to. We leave that away. There are ways around that, but for the moment, it's not. It's what we're up to do now. That's not important. It's just all I'm saying is there's a graph representation of the joins and the where clauses. So that's called the join graph or query graph. And now what we do is we start computing, we compute these different join orders using dynamic programming. I guess most of you have seen some sort of dynamic programming. It's based on two concepts. That's the main idea. How you do is you start computing an optimal plan for each input relation, and then you grow those plans into bigger plans. So basically, if you have 4 input relations, you first start computing what is the best plan. If I only had one relation, if I only had A, what would be the best plan? Would it be the scan? Would it be the index axis for A? Whatever. What's the best plan? So you basically compute that for each of those 4 relations independently, and then you start making those problems bigger. Then you say, okay, I have an optimal plan for A and I have an optimal plan for B. What if I just do a join among those 2 optimal plans? What would be the best possible plan? That's what we're doing in dynamic programming. So basically, we have 2 requirements here, and one is requirement 1 is we have an optimal substructure. That means a problem can be divided into smaller parts that can be combined into a globally optimal solution. So it's kind of like in divide and conquer, where you not only conquer, but the different parts you're acting on. Yeah, you divide it into subproblems, and the different parts you're acting on are later on also assembled together to form a globally optimal solution. Yes? And that only works if you have an optimal substructure. So you can divide the problem into smaller problems. You solve the smaller problems optimally, and then you can reassemble them to come up with a globally optimal solution. That's this first condition. The second is overlapping subproblems. So you see solutions to subproblems many times, but you only compute them once, keep them in what's called a dynamic programming table, and reuse them whenever possible. And how would that work for this example? That is visualized in the following. And this is a very textbook style optimization you will find in many textbooks. And we will optimize that in different steps. In particular, for the moment, we will completely ignore the graph structure. I wrote it down on the left here to tell you what the query is about, but basically I will ignore that because that's how the basic dynamic programming algorithm actually works. So first step is we look at problems of size 1. Size 1 means just one input relation, and that's marked here. So with this bitmap or bit list, I basically mark what are the relations considered in this particular subplan. So this row means I only look at plans for relation A. And those are my different plans. Here, I could do a scan on A. I could do an index access using whatever, maybe that's an unclustered index. I could do an isom access. Yeah, those are the different plans I'm enumerating that are possible here. And I do that for each and every of those sub-problems of size 1. So for B, maybe it's also a scan. You can always do a scan, of course. Yeah. So here scan, 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 of course. And depending on whether an index is available or not, you might be able to access an index. So recall again, at this point in time, you better have a catalog telling you, okay, which indexes exist on which relation and on which attribute, because that's the information you need here at this part of the optimization process. Well, then once we have that, we look at bigger we can prune plans based on cost estimates where we believe that are not efficient. So here you have 3 candidate plans that are possible, but now you only keep the one that has the lowest estimated costs. Yeah, and that just in this made-up example might be those plans. So here it's the iSeek on A1A and so forth. Here it's the scan is cheaper than the index access. Yeah, or maybe there was an unclustered index, whatever. Yeah, that's basically based on estimates, based on cost models that tell you what are the expected costs. You can determine what are the best plans, or you expect to be the best plans. Well, then we are here. So basically we pruned all the slower plans, the plans with higher costs, and now we're here. And now we start iterating. Basically, we now look at plans of size 2. Those are the different options that exist here. Basically, we can look at plans that combine A, or plans concerned with relation A with plans with relation B. Well, and here we don't, that's a trick here then, of course, in dynamic programming, that, well, you already have an optimal plan for accessing A only. Yeah, you have an optimal plan for accessing B only. So it's just a matter of combining those 2 optimal sub-plans. Yeah? So that's why here I picked the optimal sub-plan for accessing tuples in A. Yeah? We saw it already here on top. And that's the optimal subplan for accessing tuples in B. We saw it already here on top. And then you can think about the different combinations. Yeah? You can think about, okay, I combine those 2 subplans using a simple hash join or a merge join or a whatever join. Whatever join operators, join algorithms are available in your specific system. Yeah? That's what you do. So enumerate the possible options here for all these sub-problems of size 2. And then again, well, you have to do estimates. For each of the options you enumerate here, you have to determine the costs. You kick out the ones where you feel like they're not efficient, and then you end up with a list, maybe this one. Maybe you say, okay, those are the most efficient plans for sub-problems of size 2. From that, you look at problems of size 3. Yeah. So here, if you look at a scenario like that, recall that, well, how can you get to a scenario factoring in relations A, B, and C? That's everything where there's A and B plus a join to C, right? That's one specific join order already. That's telling you, aha, it's the first join on A, B. That's this one here. And then you join it with C. That's exactly what I'm doing here. Actually, the CP means I'm doing a cross product, because there's no edge available. Yeah? If you look at the graph here, A and B had a join predicate here, and now I'm joining it with C. I only have these very thin, narrow lines visualizing a cross product. So basically, that is why I have to use a cross product here. Yeah? And that's one way of getting to this to a plan for these 3 relations. But of course, a different way could be to use this plan here, this plan, and then that should be joined or cross product with B. That would be another option. Or what is the other option? This plan here, yeah, joining it or cross producting it with a plan on A. Yeah? So I have many different options to get to a plan factoring in A, B, and C, using or reusing the optimal subplans you already computed. And that is why we keep the optimal subplans in a dynamic programming table. That's what I'm displaying here with this table. Yeah, and then you have these options, and eventually that's the last option you have. You again prune the ones, and based on that you can come up with a plan that is optimal for 4 relations. So again, you could now enumerate plans of size 4 and then pick the with different options, pick the one that has a lowest cost under your cost models. And here's a pseudocode for that. So basically the input to this algorithm is the number of relations, then the cost function telling you for each candidate, for each subproblem, what is the expected cost. And then basically you start by first creating plans of size 1. Those are the axis plans I showed initially, and then you prune out the ones that are not efficient. And then you iterate over the different plan sizes in ascending order from 2 to n, and do what I just explained in the example. Yeah, that's basically the core idea of this algorithm. Okay, and yeah, so one problem with this algorithm is that it lacks, or it avoids 2 opportunities for optimization. And one is it ignores so-called interesting orders. What is an interesting order? An interesting order is something that's not expressed in this graph as such. As this graph, well, you say if a yellow edge is a join and those are selections, you remember the relational algebra, in the relational model I said there's no order among tuples. Order doesn't have a meaning, it's not defined in that model. However, you may remember from last week, hopefully, that we talked about a sort merge join. So whenever you apply a sort merge join, the resulting tuples of that join are ordered along the join predicate, along the join attributes you used. Yeah, it uses sorting on the 2 inputs to perform the actual join, and that has as a side effect the result of that join is sorted. And that is something that might be very interesting if you have many different joins. So what we want to do is something like that. Assume a situation as follows, where you now are in dynamic programming and you want to assemble a plan of size 2 among relations C and D. So assume I had for C that is the optimal plan, and for D that is my optimal plan. Yeah, I seek 2AD, and I basically what I'm doing here is I'm tearing apart the join operation. Maybe I scribbled that briefly down on my iPad to show you what's going on here. Let's move to the iPad. So basically, that's the situation we're in here. We had the sort merge join operation, and you could write it as one bubble. Huh? Sort merge join. One bubble, that's one operator, and has 2 inputs. Let's say R and S, and they produce a result. Yeah, the effect is, the result is sorted on the join condition. So if you have whatever R.id equals S.id, so basically as both inputs are sorted, the tuples are also sorted with respect to both R.id, S.id. I can only write up, I mean it's equality anyway, so that's redundant. They're sorted with respect to the ID attributes. So, but this sort merge join could be written differently. I could say, well, actually it's like these 2 steps, right? I mean, we have a merge join where the sorted streams are merged, and in front of that we have a sort operation on the join attribute. We have 2 of those sort operations actually, and here's the input. Okay, and we have the same conditions here. They're sorted on R.id equals S.id and so forth and so forth. But basically here, that's a merge join, already assuming the 2 sorted input streams. So. And now the situations we're looking at is, what if the stuff is already sorted? What if we operate on an input where the input is already sorted on the join attribute? Then I don't have to sort here anymore. Then I could get rid of this sort operation because it's already sorted. And there are many opportunities in databases for that. in particular, here in this example, here, if you look at this plan, index sequential access method, if you remember, so that's a clustered index that's already sorted on ID. So the data is already sorted on ID, and if that is my join key, I don't have to sort it anymore. I can skip the sorting skip altogether. And that's basically what's depicted here. So this plan is saying, well, yeah, it is sorted already. There's no additional sort operation required here. However, on the right input, I'm calling the sort function here because the results of this iSeek are not sorted yet. Yeah? Therefore, here I have to sort. On the left, I don't have to sort anymore. And that is exploiting the property that this isym method delivers data in sorted order. And that we didn't express that before. So basically, what we did before is we said, okay, for each and every plan, we only consider one solution. The solution that gives us the smallest costs under the cost model. Yeah, and basically what I'm changing here is that I'm saying, maybe if you go back, I think the interesting thing is I can tell you if you go back, if you go back to this part here. Here, that's the situation. That is where we didn't look at the interesting orders. So what happened here? I said, okay, we have all these options. Now we take the cost model and we only keep the one option, the one solution that has the lowest expected cost. And that in this example is this iSeek. And I'm discarding this isym method. Why? Because this iSeek is faster. And the change I'm doing now, if I want to consider interesting orders, is to say, hold on a moment. I know that this method outputs stuff in whatever order, I have no idea. But I know that this access method, the isym, outputs results in order. So the plans, even though they on the relational algebra level, return the same tuples, the one has the additional physical property that the tuples are ordered with respect to a specific key. And now the trick I'm playing is to say, okay, I run the same algorithm. However, if I know that the specific solution for such a subproblem has a specific physical property, I keep it in the algorithm. So what we do in the following is I know this is a special case because it has this physical property, so I keep it as well. I not only keep the smallest overall plan, but for each physical property, I keep the best plan, the fastest, not the smallest, the fastest plan I have available. And that's the difference to the slide we have here, where, so that's what I showed above. They are discarded. And now I say, no, they're not discarded. This has a different physical property, a so-called interesting order. And that is why I can consider it in when assembling the larger plans as well. That's an important change you're doing here. And sorting is the most important, interesting physical property that may exist there. Others, like data is already partitioned. Those are the two important ones. There's a long story behind that. We just wrote a paper about that. Long story. But the most important here is sorting in interesting order. Okay, so when you do that, you can insert merge joins and you can exploit available orders, and that may lead to different solutions in the overall best plan. Another thing one should do, and if you think about it afterwards, it's clear that one should do it like that, but yeah, I don't know. Some explanations do it like that, and basically that's why we showed it to you like that as well, is that why do I enumerate plans that contain a cross product anyway? I know a cross product leads to square complexity. That's super expensive, and that's not going to fly. Huh? In particular, if you assume that for each and every input size, a join will be faster than a cross product, which is not entirely true. If the inputs are really small, a cross product, these two loops, is much faster than initializing hash table, inserting it. Yeah? So the cross product may be a little faster, but it's a little difference. But if you think about the join graph, So why would we even enumerate stuff where there's no joint predicate? And that's basically the next important extension in dynamic programming, where you say, I'm not going to enumerate problems that cannot be connected by a join. So basically, you saw that in the dynamic programming tables, you had this cross product, cross product, cross product. We're not going to do that anymore. We're going to say in the moment, no, we don't have a plan for that. Let's ignore that. So basically, what I'm suggesting is you traverse the graph just along the existing edges. And that yields a very efficient algorithm. That's basically state of the art. So in this example, basically, you could make a decision, okay, what is a viable sub-problem of size 2? That is this one, joining A with B because there's a joint predicate, or joining C with D is fine, B with D is fine. Yeah, that's all fine, but C with A, no. You don't do that, you completely ignore that because that's only a cross product. And that, of course, decreases the size of the dynamic programming table somehow. It depends on how your join graph looks like. That's clear. Yeah? If, for instance, if your graph has edges among each and every relation anyhow, yeah, that's called a clique. Yeah? So you have edges among each and every relation, then you don't gain anything. But typically, you don't have edges among each and every relation, and then you gain something because you don't have to enumerate everything. Yeah? So that's a very important optimization in this world. Well, and now let's look at rule-based optimization again. Let's think about that for a moment. So initially, today, I told you rule-based optimization is an interesting technique, right? So let's go back to that one. Where was it? Here, this stuff, pushing down. Here we did this example for certain transformation steps, basically saying, yeah, you start with this canonical translation, you break up the predicates, that's rule-based optimization. There's another rule where you push down predicates as far down as possible in the plan to filter out stuff early on. Very important rule, push down selection. Well, then you build joins by combining those the selections having a join predicate on top of a cross product. Yeah, those can be rewritten to an actual join with a join predicate. Yeah. And then you push down projections. Basically, you add another projection by making tuples less wide. So that's what you do here. But now if you think about that, so what is the relationship of rule-based optimization and cost-based optimization using a join graph? That's food for thought, and it's very important to think about that a bit. So how would you do it? I mean, basically, so how would you do a query optimizer in the first place? How would you develop that? Yeah? Or phrasing that differently, if we go back to our join graphs. So if you, let me phrase it like that. So assume you don't build a compiler that, so what I showed you was rule-based optimization initially today, the textbook style optimization. What is the problem with textbook style optimization? What is the problem? Yeah, and why isn't that a problem? And and what if you did it the other way around? So assume you built a compiler that takes a SQL statement and directly translates it into a join graph rather than a canonical query. So we don't do this left deep canonical query with cross products and then rewrite the join predicates, but what we do is we build such a graph. What is the difference? What are pros and cons over rewriting it to a canonical query? That's something we should discuss a bit for the remainder of the time we have today. Any ideas? So it's two different ways how you could do a compiler. Huh? Write it in the chat if you have an idea. I can give you some hints. Yeah? Maybe just go back to the slide. I have to. So here we go. So just by looking at this slide, what the query parser does. And I wrote down a warning already here. What could be the problem with this kind of translation? I mean, say it's fine, a relational algebra is great, let's translate a relational algebra, everything fine, blah, right? We know relational algebra, how that works. That's cool. So we basically consider SQL as a front end to relational algebra. And then from that we depart and do everything else. And we say, okay, whatever. You can depict that as a tree shown on the right. You do all this magic of rule-based optimization. That's how it's taught. How rule-based optimization is taught and how many systems do it. So the discussion we should be doing here is that the right way of doing that, or is there any problem with that? Yeah, someone is writing. Let's wait for that remark. You could select first, which might increase performance of your filtering. Yeah, I'm not sure what you mean with that answer. In which approach? This one, in the canonical form, or in the other approach where I annotate the selection predicate directly with a relation? Not so sure how you mean your answer. Any other idea? What are pros and cons of this approach? Let me give you another idea. So basically he is saying, there's someone writing, basically saying, okay, relational algebra is awesome, so I translate whatever I have to relational algebra and depart from that. Yeah, so basically you make a high-level design decision to say, okay, well, those queries can more or less express the same things, so let's translate it to relational algebra or extended relational algebra, yeah? Whatever variant you seem suitable. And from there, let's go on. So very early on, you make a decision to map it to relational algebra, have it in the tree structure. Relational algebra as a tree structure. You can extend it, but normal relational algebra as a tree structure. Yeah, and then basically, based on those rewrites, try to understand, okay, which filter predicate belongs to which input relation, or how do I get rid of cross products in the first place, yeah? By having these rewrites here. That's what we have, huh? Where you get these joins. And then in the end, what do you come up with? You have a tree structure. Yeah, and from the tree structure, you could then enumerate the different joins using a suitable algorithm. Yeah, that's a high-level design decision, and you might do it like that. Versus, we did it the other way around. Just when I scroll down these many slides, I think just show you the break. That's the other. Oops, here we go. This join graph, where I said, no, I do that in one step. Yeah, I don't translate the query into a tree. I translate this query into a graph. Because in the end, it's a graph, and it can be anything. I can also have another join condition among A and C and B. So that's not. It can be. It doesn't have to be a tree. It can be a more general graph. Yeah. So what does it mean for rule-based optimization? So assume I do a compiler that I do a query optimizer that compiles it into the stuff we are seeing here on the right. On the right here with this predicate. So what would rule-based optimization give me at this point in time? Yeah, could I use rules to rewrite this graph? Let's phrase it like that. we'll wait for one more reply. Someone's replying. It's a simple question as like, do you still want to use rule-based optimization? So someone's writing, we can't really use rules like predicate pushdown in the graph. Can we? It's difficult, that's true, yeah. But they also wouldn't apply really because I pushed it down in a way. If you look at this one here, that's basically the same as pushing it down in a tree representation of the query. The filter condition on this specific relation is already, basically I have it as an annotation already in the graph. All of these filter conditions, they already are annotated. And then there's the other class of predicates that span more than one relation. That's a join predicate. What the join predicate is about, saying, okay, it's more than one relation. Actually, there are also self-joins, and you can join the relation with itself, but it's kind of, the relation is in two roles. So basically, join predicate has two relations, and that's an annotation to the edge. So all the information that was ever there in this simple sequence statement is already preserved in the graph. And you see there's no artificial machinery involved in pushing down selections and in reinserting joins. Yeah? In particular, if the joins are explicit anyhow. Yeah? So you have this join on statement. So the parser already, without looking at, without extra machinery, sees directly, oh, a join is coming up. So that must be a join predicate. Otherwise, it doesn't make sense. Yeah? You know, join predicates can also be written down in the where clause. But basically, the parser can already assemble such a join graph. And then the question is, why would I need rules in this situation? I don't need a rule to push down selections because that's already annotated. I don't need rules to reinsert joins or identify joins because I did it directly during parsing. So this is basically saying when you do this kind of translation, many of the rules go away, not all of them. So some still have a justification. For instance, if you have a transitive condition, maybe I show that briefly, how that looks like. So if we go to the iPad. So assume you're in a situation like this. Oops. Maybe you are, let's say this is R. This is S. You have a join condition r.id equals s.b. Yeah. Let's use s. Whatever, it doesn't matter, d. Yeah. r.id equals s.d. That's my join condition. And I have a filter predicate saying whatever, r.id equals 42. Well, what does it mean? That means that you can combine those two. You know, r.id equals 42, only then it qualifies. r.id equals s.d, well, then you can transitively add another filter condition to s saying, well, then I know that s.d equals 42 as well. And you can already exploit that when creating subplans of size 1, of course. Yeah. So that's the type of rule that still makes sense. In this world, other rules apply to unnesting subqueries. That's also a bit longer story. Or considering groups and having, as a group by and having. But for these simple select from where clauses, like something like that, a lot of the machinery that you typically learn about in textbooks from the 90s, let's say, they still do these rule-based optimization approaches, and they can really be questioned. So I'm saying you save a lot of effort if you don't do that, but try to directly translate to such a join graph. And then, so basically don't force it into a binary tree early on. You don't force it into relational algebra, but you keep it as a graph, and then you start enumerating on the graph, and then you can do binary things, and then you can try to find out, okay, what is the quickest, what is the best binary tree on this graph. Yeah, that's very important to do it like that. And that brings me to the conclusion for today. So basically, we have seen that the cost-based optimization is a key technique for large or complex queries. Yeah, so what does that mean, large or complex queries? Large query means many joins, yeah? Or there's a lot of sub-queries going on, then there's a group by having and another join, tra-la-la-la-la, leading to a complex query graph. Yeah? Then these techniques may apply for simple queries. Assume you do a simple lookup in a table or join two relations, doesn't really pay off. Yeah? You don't need cost-based optimization for that. Simple heuristic-based things can do the same job here, or a very good job. A very important design decision, optimizers, to my understanding, is to not force SQL into relational algebra too early. Yeah, that's what you see in many textbooks. I don't think there's a good reason for doing that. That's how it was done historically, but I don't think it's the best possible choice. It loses information that may be there, in particular if there's join on clause already. You can directly map it to joins. You don't have to remap and first call it a cross product and then through rules make it a join again. I don't think that's a very good idea. It creates a bunch of artificial problems. So that's a pattern that's also you can sometimes observe in computer science. I guess also in the real world, the way how you phrase your problem may introduce artificial problems. And another way so you've seen that here. You say, okay, it's a binary tree. And then I have to do something like rule-based. I have to find out the joins. I have to do push down, stuff like that. That's kind of artificial because you could get that directly, or many of these things you could get directly by translating the SQL query decently in the first place, by not forcing it into relational algebra, which has these restrictions. Another example in query optimization and processing is, okay, we have the graph, we map it to a relational algebra expression. Well, then Professor Dittrich said, relational algebra, the joins only have two inputs, right? That's how you have to do that. Well, what if you have three inputs? Well, then you have to have two joins, and then you have the join order problem. But what if your join had three inputs? Assume they all join on the same join key. If you had an operator that joins all of them in the same algorithm, then you don't have a join order problem. Yeah, that's another place where you introduce kind of an artificial problem. In query optimization, it's not so severe because often the joins are only are not on the same key. But if they are on the same key, then these artificial blow up of the search space may occur. So basically, my suggestion here is you should always start by translating the SQL query into a join graph or query graph. That's a synonym. And only then enumerate along the graph. So basically, what you do is you do different traversals of the graph, using dynamic programming. The dynamic programming that factors in the graph structure is basically creating different traversals of the graph, where in fact, that doesn't mean that you always have a path and then connect one relation after another. It's not like visiting the different nodes. It's really building up different sub-problems, but only the ones that are connected by join conditions. And that's different graph traversals. Yeah, that's what I wanted to tell you about cost-based optimization today. So we also have an exercise in that assignment that will be published in the afternoon. We'll meet again on Friday for the lab, 12:15, and then it's Christmas, New Year's Eve, and we'll meet again the first week of January. And there we continue with query optimization. There we look how data is passed around in between operators, different execution models that are important, particularly for memory database systems. With that, thanks for your attention. I will be around in the audio chat of Discord. Stay safe, stay healthy. See you soon. Bye-bye.